So taking a look at each of these three, notice for the first one, we know f of x equals 3. We're asked to find f prime of x. So f prime of x, of course, that's the derivative notation we're familiar with. So what is the derivative of a constant? That is just of a number that doesn't have any x or anything like that in it. F prime of x equals, well, think about the graph if you're feeling a little stuck. If you graphed f of x equals 3, that is like y equals 3, right? It would just be a horizontal line. What's the slope of that line? 0. Hence, f prime of x equals 0. Okay, the next one, g of x equals 7. So, what does d over dx of g of x equal? It would also equal 0 because, again, d over dx of g of x, that just means derivative of g of x. Same kind of thing, just a different notation. Okay, for this last one, we're asked to find dh over dx.
That wasn't one of our things.
dh over dx then would be 0 again. Yes, because, again, it's the derivative of h with respect to x. One other note with that notation, we really do read this as the derivative of h with respect to x. So if this was not an x in here, whatever that is would be the same variable down here. So we just saw the rule that the derivative of a constant will always be 0. So this should then go onto your derivative rules page. We're going to be filling in a number of items on that page today. So this is derivative of constant. Now, I want to take you back to the very first thing we added to our derivative rules. Remember how you added power rule? Remember that in power rule, we had to include that little part there about n cannot equal 0. Why? Why is that there? Yeah, so think about, like, what if we just had a very basic function? X to the power of 0. Anything to the power of 0, yes, equals 1. So if you have your variable to the power of 0, it really means that that is a constant. And the derivative of 1 would equal 0. And so the power rule works as long as we aren't trying to do it with the exponent of 0. It works for everything else. We've seen it with fractions, we've seen it with negatives, we've seen it with positives. But it just doesn't work with the 0 because we are not going to do 0 minus 1. Of course, the derivative of this does not equal 1 over x. That would be the x to the negative 1. It does not give us that. The derivative actually would just be 0 because it's a constant. All right, we're going to continue going in and out of notes because we're going to be practicing and seeing where some of these come from. Please find y prime for this function. All right, so for this one, we're asked to find y prime. So again, that's just another way of saying the derivative of the function. So we know that this one's going to be able to use power rule because I see x to the negative 3. So really what we do, remember, is I do the 12 times the original exponent. So I do 12 times negative 3. And then the exponent on the x there, we subtract 1 from it. So negative 3 minus 1 is negative 4. And then we clean it up from there. So y prime would then equal negative 36 x to the negative 4th. Now we're okay stopping there for this problem. You don't need to simplify it because our original had a negative exponent in it. Since our original had a negative exponent, your answer can have a negative exponent as well. If, however, the original was written as a fraction, so in that case it would have been 12 over x cubed, then you would, in that case, turn this into negative 36 over x to the 4th. But you only have to do that when you start with it simplified. Yeah, and so at this point, though, either of these answers is correct in this case, but if you start with it simplified, then only that answer is valid. So you notice the simplified answer is always okay. It's just the unsimplified one about knowing whether it is or isn't. Now you'll notice that in order to do this problem, we actually used another rule that we haven't explicitly stated. Because we know how to do the derivative of x to the negative 3 just by power rule. But the power rule didn't tell us anything about the number multiplied out front. We knew that from previous work we did with derivatives, where we still had the limits in there and all of that. We knew that if we multiplied it by a constant, all I had to do is multiply my derivative by the constant. So I was able to do that. But let's go ahead and add that to our rules as well. So this is the constant multiple rule. Add that onto your list of derivative rules, please. All right, so we see here the constant multiple rule. Basically, the idea is that if I have c that's multiplied by some function, I can go ahead and just multiply the derivative of the function by c, and I'll have the derivative. Notice I'm not taking the derivative of the c. Otherwise, the whole thing would become 0 every single time. Now, the thing about this rule, though, is that it looks kind of clunky. And, of course, mathematicians are famously lazy, and so we always like shorter ways to write things. Now, you don't need to write it this way, because you already wrote that rule down. But we could have written the same thing down using the d over dx notation. If we had done that, the exact same rule would have been written this way. Notice what it does for us by writing it with d over dx. It gets rid of the whole if this, then that kind of thing. So instead of having to write two different equations, we can write just one equation. If I'm taking the derivative of c f of x, then it's going to equal c times the derivative of f of x. And so that d over dx notation tends to be a little bit shorter, and as a result, you'll see most of the rules that we'll be saying from here written in that kind of notation. Just realize that these two statements are equivalent. They're saying the exact same thing. All right, a little bit more practice. Please find the derivative of each of these two functions. So taking a look at f of x there on the left, if we want to find f prime of x, then I need to look at this square root of 2x in a different way, because technically I only know how to take the square root of x right now. I don't know how to take the square root of 2x based on the rules that we have. However, I can actually set it up that way to where I'm only taking the derivative of x. Or the only square root of x. And that is by writing it as the square root of 2 times the square root of x. That's the exact same thing. And so then if I wrote f prime of x, but I haven't actually taken the derivative yet, so it just needs to be f of x. Now I'm going to go to f prime of x. Now the square root of 2, remember, that's just a number. It's a constant. It's a more complicated constant than just 2 or 3 or something like that. But it is just a constant. And so I'm going to do the square root of 2 times the derivative of root x. Now, what's the derivative of the square root of x? Well, let's see here. The square root of x is x to the 1/2. So that becomes 1/2 times x to the negative 1/2, which is then simplified, because the original was simplified, so I do want to simplify it here. 1 over 2 root x. Which actually I could simplify even further, couldn't I? Because I could then multiply top and bottom by root x and turn it into root x over 2x. Then we even got the radical out of the bottom. So the whole thing ends up being root 2 times root x over 2x. So then if I simplify my derivative, then f prime of x equals the square root of 2x over 2x. Now the thing that mixes up a lot of people on this one is the fact that the root 2 is just a constant. A lot of people will try to take the square root of it. This can especially become an issue later on. But remember, root 2, it's just a constant. And that's going to help you. Now on to g of x. When we want to find g prime of x, and we can actually go straight to finding g prime of x. We don't have to manipulate this one as much. Pi, I'm throwing in the pi here because, again, I'm wanting you to see the symbol, but remember that it's a constant. Because pi represents just a number. It's a complicated number, but it's just a number. And so I can just turn this into pi times the derivative of x to the fourth, which is 4x cubed. Now, I do want to simplify it a little bit because we tend not to write it like that. We tend to write it as 4 pi x cubed. But then that's it. We're done. Because remember, pi is just a constant. Continue with our practice. Please find dy over dx for this function. All right, so for this one, I'm trying to find dy over dx. I'm going to go ahead and call that y prime. Because remember, they mean the same thing. All right, so for the first one, what I hope you did is that you took the derivative of the negative 9x cubed first. And so I multiply the negative 9 times 3. That gives me a negative 27. And then that becomes x to the power of 2 instead of x to the power of 3. Then we repeat the same thing with the second term. So I do the 8 times 1/2, which gives me 4. So it's going to be minus 4. X to the power of, I do the 1/2 minus 1. That is a negative 1/2. Do I need to simplify this one? No, I do not. Because the original was to the power of 1/2. The original then was not simplified, so no, we do not need to simplify it. If you did simplify it and you just want to check, it would have been minus 4 over root x. Now, once again, though, in order to do this, we used more than just the power rule, right? We went back to some of our derivative rules that we learned when we were just seeing it in terms of limits and difference quotient. You must have to do difference quotient for every one of these, don't you? But notice, just based on the rules that we've written down so far, we didn't actually have a way to know that we could just take the derivative of each of those terms individually. So, since we knew that from before, we can go ahead and translate it to this. So, add the derivative of a sum or difference. The example is given as a sum. Of course, the rule would work exactly the same as a difference. Yes, this goes onto your derivative rule sheet. And then this one's a great example about why the d over dx notation actually makes our lives easier. Because by using that notation, we saved ourselves from having to say that if we try to take the, if we wanted to know what f prime was, where f prime equals g plus h, and having to come up with, we'd probably need like 5 different function names just to come up with it. It'd be a pain. But by using the d over dx notation, it's just easier to look at, easier to figure out. Now, big thing here though, notice that note on the bottom. This rule works like you think it should for sums and differences. We can go ahead and take the derivative of the first, derivative of the second. But we cannot extend this to products or to quotients. So for instance, if I was given, or looking to find the derivative of f times g, that would not equal f prime times g prime. It will not equal that. We're actually going to get into some separate rules that deal with these called the product rule and quotient rule later. But for now, we can know that at least for sums and differences, life is easy. Works the way you think it should. All right, now taking a look at finding this derivative, you'll notice that what we have here is we have a monomial times a monomial. And remember earlier I made a special emphasis of pointing out that we don't have a rule that allows us to deal with two functions that are multiplied together like this. Yet, we actually can find the derivative here. If I want to figure out what dy over dx is, I can actually start by rewriting this and simplifying it so that it is in a format that I'm used to working with. So I can actually multiply the two monomials. So I do the 4 times 10, which is going to be 40. And then x to the 5th times x squared is x to the power of 7. Remember when we multiplied the x's, we add the exponents. Now find the derivative of that, please. So, to find our derivative, I'm going to go ahead and call it y prime. I multiply the 40 by my original exponent, so 40 times 7 is 280. And then it's going to be x to the power of 7 minus 1, 6. So this is then done. We don't need to do anything else. We don't need to like try to put it back into the product of two monomials or something like that. We're done. So if you can simplify it at the start to make it look like something we can deal with, then you do. We're going to use that same principle for a lot of these problems going forward. So go ahead and write this one down. All right, so when we do this one, first of all, notice that I cannot take the derivative in its current format because I have a function over a function. I have x's in both the top and the bottom. And right now we can't do it without some simplifying first, but we can simplify it. So we're going to do that first. That gives me y equals, the x to the 4th over x becomes x cubed. The 3 over the 12 becomes 1/4. Now, for some of you, you might get a little thrown off here just because it's now x cubed over 4 instead of multiplying by something. But remember that x cubed over 4 is just the same as 1/4 times x cubed. So it still is following the constant multiple rule that we saw earlier. So we go ahead and address it like we normally would. So I'm going to do the 1/4 times 3x squared. Now, of course, you didn't have to do it with the 1/4 out front. Our final answer that I'd be looking for here would be 3x squared over 4. That would be our final answer. We're done.
No.
So having done those, I think you probably have a good idea about how to go about this one, although I am throwing in another wrinkle. We'll see if you catch it all. Go ahead and start working through this one, see how far you get, and then we'll work through it together as well. First thing here, though, is in its current form we can't do it, so we do want to change the form of f of x. So that means I'm going to go ahead and square the x cubed minus 5. Now remember, that means I'm going to do x cubed minus 5 times x cubed minus 5 and multiply that all out. So then we end up with 7 times x to the power of 6. Notice it's x to the power of 6, not 9 there. Minus 10x cubed plus 25. Now, we're still not done yet in terms of getting it ready just to be able to take the derivative. We still got to distribute in that 7. And so I'm going to turn this then into 7x to the 6 minus 70x cubed plus 175. Now, that's a lot easier to find the derivative. So if you haven't yet gotten that part, go ahead and find that derivative from there.
Whoa.
All right, so from here, I go ahead and I can take the derivative, finally. And so we do f prime of x equals, and we go ahead and go through it like we normally would. So I'm going to do 7 times 6, that's 42x to the 5th, minus 210x squared. And then the derivative of 175, of course, that's just 0.
0.
So that goes away. However, notice this is not our final answer in this case. Because oftentimes, you're not going to be asked to just find f of x. You're going to be asked, f prime of x. You're going to be asked to find f prime of a number.
And then you substitute.
This is looking for f prime of 1, and so we are not done yet. We need to plug 1 in for x in our final equation. So we're going to do f prime of 1 equals.
I'd say that's about negative.
All right, now for this one, notice we're being asked just for f prime of x, so we aren't going to have to plug a number in at the end. But in order to be able to find f prime of x, I got to make this original function look more like what we're used to. And right now, it looks like the product of 4x cubed times the square root of x, and that we can't work with. So I'm going to rewrite it here. In order to do so then, I'm going to go ahead and start by writing that square root as a fractional exponent. Now that I've done that, you'll notice I can now combine the x's. And so, remember that when I multiply the x's, I add their exponent, so I got to do 3 plus a half. which is 3.5, or it might be kind of awkward to write it as a mixed number like that in an exponent. So you could also write it as 7/2.
Oh, not 5.
And that's the way I'll write that then.
It's okay, Adrian.
Now that we have it this way, we can go ahead and find the derivative. So, to find f prime of x, I go ahead and I do 4 times 7/2. Well, that's going to be 4 times 7, which is 28. 28 divided by 2 is 14. Then x to the power of 7/2 minus 1. 7/2 minus 1 will give me 5/2. But of course, my original problem was given simplified. So I need to then simplify my derivative, f prime of x here as well. So the 14, nothing changed to 14. X to the 5/2, well that's like 2.5. So that'll be x squared times the square root of x. Alright, so now we're going to take a look at how we go about finding a derivative of something like this. And again, we have a function over a function, which is, in the current setup, would be really tough to do. In fact, we can't do it without the quotient rule, which we aren't going to learn for a little while yet. But we can do it just with product rule, if we simplify this fraction a little bit first. Now I'm going to show you the long way, just so we can remember why it works the way it does. Because I can start by splitting each of these different terms from the top into their own fraction over the denominator. And then, of course, we can simplify. So we can go ahead and simplify then. So then f of x will equal 3x to the 6 for that first term. That's a lot easier to work with now. Then for the second term, 9x cubed. Now for that last term, though, there's nothing really we can do to simplify that.
Oh, yeah, we can. Can you just...
Now we could write it as 5x to the negative 2 right now. You could write it that way to make your life a little easier. But that's just rewriting in a different format, not necessarily simplifying. So either way is fine with that piece. Now at this point we can go ahead and find our derivative, which is just the derivative of each of those individual terms. So 3 times 6 on that first one gives me 18, then x to the 6 minus 1 is 5. Okay, so I got 18x to the 5th minus, now I do the 9 times the 3, 27. And that's x squared. Now for this last one, this is where it might be a little bit easier on you if you wrote this as 5x to the negative 2, because I'm going to be multiplying the 5 times negative 2, so it's actually a negative 10 x to the negative 3.
Oh, so it'd be minus.
And so then, everything stays the same after I simplify it, 18x to the 5th minus 27x squared, except for this last part, which I'll write as 10 over x cubed.
That's not that bad.
So it looks really scary at first, but actually it's pretty doable. Now, any other notes on this one? Again, if you want to write this as 5x to the negative 2 at that point, you're welcome to. That can make your life a little bit easier. In this case, did I need to turn this into this? Yes, I did, because the original was written with fractions in there. And finally, the original was written as one big fraction. So do we need to turn this whole thing then back into one big fraction? No, we don't have to. You can, but no. I'm not going to make us go that extra step right now. We don't need any layers of complexity. We already got enough right now. All right, so having seen that one, let's take a look at how we go about doing this one. So for this one now, again, I want to be able to break it up. But in this case, breaking it up just by like writing it as like 2x squared over 2x minus 4 and so on, it's not really going to help us. Because I still would need quotient rule in order to be able to find these derivatives. And I don't have quotient rule.
Why can't you just give us quotient rule? You just never get it powerful.
All right, but we can actually do a little bit of simplifying here. Because the top of this fraction and the bottom actually both factor. So please factor both your numerator and your denominator. Now the nice part about this one is that after we factor it, you'll notice that there's some reducing we can do. The x minus 2's cancel out. And when we cancel those out, the derivative that we're finding is actually going to be much easier, because then it's just 2x minus 3 all over 2. Or, if it's a little bit easier to look at, 1/2 2x minus 3. Or, if that's even bothering you to look at, you could always turn it into x minus 3/2. All of those are equal to the same thing, so any of those would work. So, find your derivative, f prime of x. See what that gives you. And so, we first do the derivative of the x. I'm looking at this one at the moment because it looks like the easiest to look at. The derivative of x is 1. And the derivative of negative 3/2 is 0. So that goes away. So f prime of x equals 1. Now you notice in this case, we're actually supposed to find f prime of negative 1.
Literally impossible.
Well, f prime of negative 1, if I plug negative 1 in for x, there is no x to plug into, so it's going to stay the same thing, so it equals 1.
Just put 2 in for A.
So this problem is asking us to find the instantaneous rate of change at a equals 2. Now, we've seen problems like this plenty of times before. Our general rule of thumb was difference quotient. Find the limit as h approaches 0. And then once we found the limit as h approaches 0, we could plug in the value of 2 in for x to see what that gives us. However, when we find the limit as h approaches 0 of the difference quotient, remember that was our definition of what a derivative is. So really, when we say instantaneous rate of change in all the different forms it can take, like velocity and how fast is it changing, all those little detaily things, all those different ways of saying it, they all mean instantaneous rate of change. How fast it's changing at that moment. We're going to find the derivative. And so, what you want to find here is, what is r prime? Well, first thing you want to do, go ahead and multiply out the parentheses, because in the current form we can't do it, but if you multiply it out, then you can go ahead and find that derivative. So, do so.